Now it's working. Okay, there we go. Cool. Good to see you all. Oh, that's not right. Oh. See, this happens when you reuse slides. Then, like, something weird happens with the slide master. Oh well. So this is in fact not the CVPR tutorial on neural fields, in case you hadn't noticed. Cool. So today we're going to talk about the second instance of neural networks for prior-based inference, which is the topic I'm most excited about. There's also so much happening here, and I'm actually, over the past 2 years, I learned so much about this topic that, or even just in the past year since I last gave this lecture, I learned so much about this topic that now, I look at my old slides and I'm like, oh, actually, I would do this completely differently now. But we're going to try, I did do some of that, so we're going to try discussing that. So again, please feel free to interrupt at any time, and let's discuss these topics that we're up here and try to really understand them. They're much more general than the things we're discussing here. And they really are related to anything that has to do with machine learning. Okay, so first, there's a project. This class has a final project, as you know. And the project proposal is actually due November 9th, which is in about, 3 weeks? The project, you will have about 1 month time for the final project, right? So the project proposal is due on November 9th, and then the final project presentations are on December 12th and December 9th, I think. So that means that you have to start thinking about that. And here's a few things for the project. So the first step in the project is going to be the project proposal. And the project proposal is really very, very slim, right? The point of the project proposal is that you think about a project that you're excited about, that is tractable, that is feasible in 1 month, right? I'm not expecting the world. I don't expect you to write a CVPR paper. I'm expecting you to pick one of the concepts from this class and either apply it to a project from your domain, or just play around with it. Honestly, like run an existing thing on a new data set that you generate, and maybe analyze it in a little bit more detail, try to make it break. So please come to my office hour if you want to run a project idea past me. Just show up in my office hour. I'll spend time talking through with you. Maybe I'll even make another office hour just so that you can come by and talk about your project proposal. But here's the form of the project proposal. It's 1 to 2 letter pages, and when I say 1 to 2, I literally mean 1 to 2. I mean 1 is also fine. It doesn't have to be 2 pages. I'm not going to give you extra credit if you write 2 pages. In fact, I'm going to be slightly more happy if you only write 1 page, because then I only have to read 1 page. But if you do need 2 pages, that's totally fine. So it's 1 to 2 pages. The sections are going to be as follows, and I'm literally going to give you points for each of these sections. So you better stick to these sections. Which makes your life easier, because so you just basically have to have these sections. So there's going to be abstract or problem definition. What are you trying to do? Very briefly, right? Then brief related work. How is it done today? What are the limits of current practice? And this, I do expect you to actually do a little bit of literature analysis, by which I mean if you, for instance, say, oh, I'm going to do something with dynamic 3D reconstruction, which we haven't talked about yet, but I want to do dynamic 3D reconstruction, then I expect you to at least find 10, 12 papers from maybe recent or not so recent past that have tackled that problem, and briefly say, oh, this is what people have done in this field. Okay? And then you want to say, with respect to the problem that you want to solve or the problem that you're looking at, what are maybe limitations, or what is the problem that you're interested in illuminating more? What's the problem you want to analyze more? Why is this analysis missing in related work? Any of these things are good. Then the proposed method. So what do you want to do specifically? So what analysis do you want to run? What analysis do you want to run? Or if you want to propose a new method, or you want to change something about an existing method, then how do you plan to do that? I think that's relatively self-explanatory. Why is it interesting? This can be very short, but just if you solve this, who would care? Why is this an interesting thing? Can be totally self-motivated. You can be like, oh, this is interesting because then we would understand this thing better, and that's interesting to me. Okay, and then these 2 things are actually also important. I want you to describe the first simplest experiment that will show you if your idea has any merit, and that is to protect yourself from a thing where you're like, oh, I'm going to change these 15 things, and then in the very end, I'm going to evaluate if it did better, but then you never get to changing these 15 things. or the whole thing that you built just doesn't work, and then nothing works, and then I can't grade anything, and that would suck. Instead, what is like the simplest thing that you can run, and if it works, you can ideally, that even if only that works, you can write your proposal about your final project report about that, and everyone will be happy. I can grade that. So what's the simplest thing that you are like 100% certain you could get to work, basically? And when I say get to work, it doesn't mean that it has to, let's say you propose a change to the method. Ideally, of course, the simplest experiment already goes in the direction where you take an existing method and you modify it slightly. But it's also fine if the first experiment is just you reproduce something that someone else has done. Just you have a tangible outcome. Like you have ran something and you can report something. And then finally, what's going to be the final experiment? So like if everything goes well, what will you be able to show? Yeah, and I think you can definitely fit this on one page. Any questions on the project proposal? Also, just to be perfectly clear, I'm not gonna, this is not supposed to be like hard or like okay, what's the point of the project? The point of the project is that I want to give you the chance to apply something, anything that I'm going to force you to apply something that you learned in this class. It can be anything related to this class. And I want you to just apply one thing that you get from this class and play with it a little bit to just understand one of the concepts that we discussed in the course a little better. That's the point. And that's my motivation for this, right? Any questions? Yes? Yes, I do have accommodations for compute. Good point. I'm going to announce that on Piazza. I think everyone has $50 off Google Cloud Compute from me. But that is quite significant. You can like run an older GPU for like a long time with that. So you can definitely run GPU workloads with this. But you're not going to be able to train a 9 billion parameter vision transformer. So, and if your project involves that, then I would suggest pick another project, unless you have compute available. You're also free to use your own compute, but I don't expect you to. So compute is something you should consider in your project as well, therefore. Yes?
So if I'm currently working on a city here, possible to like start to convert, assuming that I'm the first author and did most of the stuff on my own.
So usually the policy is that, it's okay if the project that you do in this course is related to your research, and that is even encouraged because that's kind of the point. And it's also okay if you use the stuff that you're doing in the course of this course in your paper, but the project report can't just be like a shorter version of the paper. Like you will have to identify something specifically that you ran specifically for this project. So you can't just be like, I take my paper and I rewrite it a little bit and then I put it in there. I would be upset about that.
Gotcha. Yeah, for sure.
But yeah, if you pick something and you're like, okay, this is maybe an analysis I wouldn't include in the paper anyways, or this is something that would be fine.
Gotcha. Thank you so much.
Other questions? Okay, if you have any concerns, please reach out to me. Otherwise, due November 9th, so it's going to be submitted on Canvas, and then we're going to review it. Yes? Yeah, it's going to be uploaded on Canvas. The CVPR 2022 template, David is, I think, uploading it right now or has uploaded it to Canvas. So you can download it and then just get started.
Okay. So when we submit it, you're going to review it and then give feedback. And then
yes. Yeah. But because be aware of the scope that you can propose, right? You're going to have 1 month of time for this thing. It's very little time. So it's fine if the scope is very tight. It can be a small thing. So for instance, right, like let me give you an example. One thing that doesn't require much compute and that is also really exciting is all of this depth warping stuff, self-supervised monocular depth estimation that we discussed, right? So imagine, for instance, here's a good example. So one thing that would be a great project, and that probably also doesn't take too long, is if you implement like a tiny version of any of the projects that we discussed in this class. That is a great project. So for instance, right, maybe you know TinyNerf. So there is this little Colab notebook, which is TinyNerf, which is just one Colab notebook, which is a tiny implementation of Nerf. If you did a tiny implementation of any of the papers we discussed in class, I would be super happy with that, right? And that is like a very So for instance, tiny self-supervised monocular depth estimation with like, here's either with a synthetic data set or you take a video data set from the internet and you just implement it yourself and you play around. Fantastic. Even if you do nothing new, if you just build a tiny implementation of that, I would be very happy with that. Does that kind of make sense? That's kind of the scope and expectation. You can do more if you want, but I would be super happy with that. Yeah. So ideally, you do it such that I can use it as a homework assignment next year. So that gives extra points. No, mostly joking. Okay, cool. Any other questions? Great, then we can get into it. Okay, so last time we talked about prior-based inference. So first we were looking at without any neural network, no machine learning. The first part that we discussed in this course is we built a differentiable renderer, and then we fit a single scene representation to a single scene. And then we said that is kind of a type of inference, right? We said, well, it is a type of inference because what we're doing is we have observables, which are pixel colors, and then we're doing inference. We're doing this optimization thing to get the geometry and the 3D appearance of the scene. And then we said that's great, but it doesn't work if you just have a single image, so incomplete observations of the scene, because then when you try to do that, the thing that you get out is just complete garbage. So for instance, if you try to fit one of these scene representations to a single image of this toy car, then you just get nothing out because the single image doesn't have any 3D information in it. Then we said, okay, how can we fix this? And we proposed this general framework, and this general framework basically looked like a little bit like an autoencoder, right? We said, okay, we're going to have a set of images. We're going to build some kind of encoder. The encoder is going to output a bunch of latent codes or a single latent code. And then we're going to build a differentiable renderer and a scene representation, and we can train that end to end. And then we said, well, in today's lecture, we're going to continue our discussion of this general framework. And we already touched on the core topic of today's lecture last time at the very end, but it was a little rushed, so we're going to get into it again today. The key questions are like how do you design the statement space? It turns out that the way you pick to represent your 3D scene with these latent codes is very important. How do you design the encoder, of course? And then what kind of scene representation do you pick? So these are all interesting topics. And these are all topics that are actively researched these days. So expect that at CVPR, there's going to be hundreds of submissions on basically different instantiations of this exact framework where people use transformers or they do this and that and very up to date. And then we discussed the first maybe interesting topic was about the inference algorithm. So we discussed something that goes into this box here. We assumed in this case that the discussion that we made is we said, okay, imagine it's like an autoencoder. We have a single latent code that represents the whole 3D scene, like a single 3D object. It's like a single latent code, 512 dimensional or something. How can we get at that latent code? And we discussed two things that can go into this box. And one of them we called them encoder-based, and one of them were called auto-decoders. And just a brief refresher, encoders basically said, let's say we have an image. The image is the green thing on the top left. You push it through an encoder, like a convolutional encoder. It gives you a latent code, and then you use that latent code to reconstruct your 3D scene. You could, for instance, take that latent code and predict a voxel grid, or you could take that latent code and predict all the weights of a nerve or anything like that, right? So that's like encoder-based. And then the other alternative was auto-decoder-based, and that was the one that was a little maybe, this is less widely known and less widely appreciated, but there the idea is you don't have any encoder at all, and instead you at training time, you have one latent code for each of your training examples, and you basically just decode them, and you optimize the latent codes jointly with the rest of your model. And then at test time, you freeze the model and you optimize only a new latent code. So I'm just refreshing everything. Does everyone still have this in mind, or did any questions pop up since you last thought about this? Yes?
Yeah, just thinking about the fact that you need one latent code, what seems like you can't train on the large data sets.
No, you can. Good question. So the question was, because you have to have one latent code per training example, seemingly you can't train on large data sets, but like imagine you have images, right? An image is much larger than the latent code. So you have to store the images. It's not a lot of overhead storing like even a 5,000 dimensional latent code in addition to storing the image. But there are other practical problems with you are nevertheless right. Actually, okay, so I should have said you are actually correct. It is very hard to train audio decoders on large data sets. That's kind of beyond the scope of this class. The reason for that is, however, not that it's expensive to store the latent codes. The reason for that is that so one problem that happens, let's imagine I give you 1 million images, and for each image you have one latent code. Let's say in every batch you sample 100 images, right? You sample 100 images, and you sample 100 of these latent codes. The problem is that in every batch, you will only update exactly these 100 latent codes that you sampled in that batch. And that is a problem because it basically means that effectively for your latent codes, the learning rate is really small because you only sample each latent code in expectation once every, I don't know, 10,000 gradient descent steps, right? So you'll only update each latent code every time you sample it. But if your data set is really large, unless your batch size is also humongous, you'll only sample each latent code very few times during training. So that's a problem. Versus with encoders, right, what happens is because the latent code is the output of the encoder, and in every batch you're updating the encoder, the optimization is much faster. So effectively what that means, one way to think about it is kind of that with autodecoders, the learning rate for your latent codes is tiny if the data set is very large. So in practice, there are problems with training autodecoders, but we're not talking about it because it's like, this is something that autodecoders might be relevant to a research project that you guys do, but I think then you just have to dive a little bit deeper into the literature on this topic. Great question, though. Yes?
I guess also in test time, you need to run this like whole optimization.
Yeah.
Pretty expensive to grade.
Yeah, that is also certainly true. You have to run optimization-based inference at test time. Yeah. And that is more expensive than a forward pass through a model, usually.
Is it like
So I think this question is like, I don't know that anyone has ever really tried. Like, I have tried before, like to make it fairly fast, and I could get it to be pretty fast, like less than a second for sure. But less than a second is still relatively slow by some standards. But you can get it to be relatively fast for small models. I actually don't know what happens with like really large models. Yes.
And so during that optimization process, you're only optimizing on one image, right?
No. Yes, you would. Yeah, in the single image case, you would basically say, do we have a slide on this? Oh, yeah, actually, maybe we do have a slide. Yeah, so just a reminder, right? So here is one model you could build. So this is just putting something in each of these boxes. We discussed each of these boxes before. So you pick a convolutional encoder, put it into the inference box. Then you say our latent code, we have a single latent code. So this is like a convolutional encoder. And then we're going to use this latent code and we're going to use it to predict a neural field. We could do that with like this hypernetwork thing we discussed, or you just concatenate it to every input coordinate. Does that ring a bell? Or was this topic confusing? Who understood that part about like hypernetworks and stuff? Or okay, good. Good. And then once you have this, right, you could build like a volume renderer or a sphere tracer. So you could just plug each of these parts together. And then like here's what this looked like, right? So yeah, I should have showed these before in our discussion. So you train this thing, and here's the thing that you can get with a single convolutional encoder, and it looked pretty reasonable. This is actually a model I trained for my faculty talk, because this was a result I showed in my faculty talk, if you were wondering. And then we said, oh, but it doesn't do out-of-distribution generalization, which was the important part. And then that was our motivation for discussing autodecoders, right? But yeah, just with respect to the question we just asked, yes, this is very fast. You take this image, you do a forward pass through the encoder, and you're done. The forward pass through the encoder is really cheap. Very fast, done, great. And then we said, well, this is kind of bad. Like, why does this model not generalize to out-of-distribution poses? And we said, well, this is because the convolutional encoder doesn't generalize. It has never seen an image of a car up close. It was not in the training set, completely out of distribution. What is it going to do? Is it's going to explain this image with the closest thing it has seen in the training set, with this, like a Hummer or Humvee or something. Okay, and that was our motivation for this autodecoder. And then the autodecoder kind of solved this issue, like because, and this is kind of a contrived example, but not that contrived. It was because the autodecoder uses the renderer also for inference, and the renderer knows about the camera pose. So the renderer doesn't care where the camera is at test time. Right, and then we did single image reconstruction, right? So these were just some results. So like here's a single image, and you can reconstruct it with this method. Great, and then you can also interpolate stuff in the latent space. So we've trained this model here on chairs, and then we interpolate the latent codes between different chairs. Great. And now, okay, so wait, were there more questions on this topic that we discussed last time? So all of this should now be kind of make sense to you. So if you have any questions, ask them now, or remain forever silent. No, great. Cool. Then we said, okay, so like this is something that people did, and now I want to discuss one new thing that we skipped last lecture, but it's actually kind of this particular instantiation isn't that important, but the general concept is very important, and it's good to think about. So let's say you remember when we trained these autoencoders on MNIST, and we could show this latent space, right? And we could show that on MNIST, the autoencoder latents like inform you about what digit you encoded, remember? So the latents really learned something useful. And that was the whole motivation for autoencoders in the first place. The assumption was we can use these for self-supervised learning. We can encode all of these images, and then the autoencoder learns something useful because it has to do compression. So now an interesting question you can ask is, what does the autoencoder learn in this case? So after we train this model, is this model useful for anything other than reconstructing 3D objects from a single image? And the answer is yes. Let me show you why. I showed you this latent space interpolation last time already, right? So I showed you this latent space interpolation where we're interpolating between different cars. So these are all different cars that are reconstructed with this model called scene representation networks. And these are renderings of these cars. And now we're just interpolating between these latent codes. And when you look at these interpolations, like imagine for an instance the alternative ways this interpolation could look like. One alternative way this could look like is that the car stays identical for a really long time, and then it just like vanishes out of existence, and then the different car pops up, right? That's one way in which the latent space interpolation could look like. But that's not what it looks like. Actually, it looks like this. And what you can see is that each car changes smoothly into each subsequent car, right? And last time I pointed out the wheels. So like, let's take a look at the wheels, right? So you see the wheels here, and notice that the wheels stayed the wheels, which maybe in this case wasn't that surprising because the wheels were at exactly the same position. But now we're changing into this long limousine, and you can see that the wheels still stayed the wheels. So like, it's not like the wheels went away and then they popped up at the ends of the limousine again. They changed smoothly from one to another. So now I'm going to ask you a question. What does this tell you about what this model has learned? Does this tell you anything? Yes? Yes? Good, yeah?
Like the neural tangent. Gradual change between
Yeah, good, good. I like that. So I mean, maybe an obvious statement. So an obvious statement is that this model knows which parts of these cars are in correspondence, right? The model knows that the wheels of this car correspond to the wheels of the other car. And when I say knows, I'm not like trying to humanize this model. The model knows nothing, in fact. But like a better way to put this is that the features that the model has learned, like somewhere in either in the latent space of the model or somewhere in the activations of this model, you will find features where the similarity of the feature between the two wheels of these two different cars is similar. So when you sample your model at the position of the wheels, somewhere the model has to know that these are wheels. Okay, so this is in fact this is the first project I ever supervised. This was an undergraduate, Amit, at Stanford, and we submitted this paper to 3DD. It's a very small paper, but here's the key idea. Let's say the key idea is basically to say, think about semantic segmentation, right? So what does semantic segmentation mean for images? Semantic segmentation for images means that for every pixel, you're predicting a semantic class, right? In other words, what are you doing is you're predicting a function that maps every 2D pixel coordinate to a semantic class. So in 3D, you can do semantic segmentation. It's exactly the same thing. What changes? Now for every 3D coordinate, you're predicting the semantic class of that 3D coordinate. So in other words, we can just neatly package that into the same kind of scene representation framework that we previously used also for geometry and appearance. So just like we can take a 3D coordinate and map it to a color and a density, we can also take that 3D coordinate and map it to a semantic class, right? like an indicator or something. Great. So this was exactly what we said. We were like, okay, let's do exactly what we just discussed. We trained this little model on cars, but now we're going to have one head which predicts the color, for instance, and the density, imagine, but also one that predicts like a likelihood for different classes. Now, oh, did I skip these slides? Okay, so now, no. Okay, so now I removed this slide for some reason, but now you could train this model in two ways. One way you could train this is you could collect a large data set of semantic segmentation masks, right? Because, of course, then you could just train it, and you could train it in the same way that you train the color model, right? For each image, you have colors and you have semantic segmentation, and then when you render the image, you render both the semantic segmentation mask and you render the color, and then you just supervise both of them. Does that make sense? So that's the easy way of training it. You just collect a large data set of semantic segmentations for each of your images. But the question is, can we be a little bit smarter about this? Because the thing that I just showed you tells you something. The thing that I just told you is that the model that is trained on images already understands semantic segmentation. Because this model clearly already understands what the wheels of a car is. So you don't need to tell it many more times. And what we did in this paper is we said, okay, it turns out that when you train this model, and then after you have trained it, you actually only need a very small data set of semantically segmented images for your class, and this very small data set is actually sufficient to basically train a little classifier on top of the output of the model, and that will do the trick. And that totally worked, so it was kind of cool. So the insight here is just that, so I mean, you know, this is a long time ago by now, but like here you can see, I think this model literally saw like 5 semantic segmentation images of a chair. And then just with these 5 labels, so like the chairs are like, I don't know, they're labeled into like backrest, armrest, and legs of the chair. And just by giving it 5 images that were annotated with semantic segmentation labels, we could fine-tune this model to do semantic segmentation. Because the model had already had to discover this like informative latent space. And this concept will appear again and again and again, like in the next 2 years. Like just the idea, this is one key idea of representation learning. The key idea is, well, that's the whole reason why we're in a way doing this class. The whole reason why this course exists is we want to train models self-supervised on images, and we expect that these models learn something useful about the world. And this was kind of the very first foray into this, like a long time ago. Now these kinds of models, of course, look a lot better, and we'll look at some that look much better. But this is, even with the simplest model, even the model that you're going to train in homework number 3, you could observe something like this. Yes? Yeah. We have done that. The paper, we're going to discuss the paper in the class, actually. It's called Distilled Feature Fusion? Feature field distillation. That's what it's called. So yeah, we've done that, and yes, you can absolutely do that, yeah. But note that if you take Dino, then of course you first need to train Dino. So you assume that you have a pre-trained Dino. But yeah, other than that, it would totally work, yeah. Cool. So just a little thing to keep in mind. Cool. So then now we're going to discuss this topic one more time last time, because I think this bears repeating. So this only generalizes to non-compositional scenes. We said like, okay, so you can do this for single objects, and I spent a lot of my life trying to fix this, but I couldn't because I didn't understand this at the time. But with this kind of framework where you encode something into a single latent code, at least with the kinds of models we were discussing so far, you would not be able to represent rooms like this. It's just not in the cards. And we said, why is that? We said it's because naively, the dimension of this latent space, like of the true latent space, gets exponentially larger the more objects you add, because each object adds degrees of freedom. And if you have a single object in your scene, that single object, let's say, has 1,000 degrees of freedom, so no problem. But now if you add a second object to your scene, now your 3D scene actually has 1,000 times 1,000 degrees of freedom, because for every car number 1, you could sample a different car number 2. And what actually happens here is kind of the curse of dimensionality. If you keep the size of your data set constant, like let's say you have 100,000 3D scenes, and the 3D scenes go from a single car to 2 cars, or from a single object to 2 objects, then suddenly the size of the data set you would need to fit that kind of model would increase drastically without any additional structure in the model. Did that kind of make sense in the last lecture, or were there confusions about that? Great. Okay, and then we said, and now we're going to talk about this local conditioning a little bit more. This is what we're going to spend most of our time on today. So we already talked about like one version of this yesterday. We're going to review it one more time. So we said, okay, what is the idea of local conditioning? The idea of local conditioning is to say that the way we're going to represent our 3D scene is not by a single latent code for the whole 3D scene, but instead we're going to spatially arrange latent codes. We're going to have a different latent code for every spatial coordinate, more or less. So for instance, we could take a voxel grid and we take this room, we discretize it into a voxel grid, and in each voxel we're going to store a latent, and then that latent is just going to encode whatever is in that, at that scene, at that local coordinate. That makes sense, right? Okay, so that in itself doesn't fix the problem. The second part that you need to be able to reconstruct scenes that are compositional is that you need a special encoder. So you need to build an encoder that preserves a certain property. So let's talk about that one more time. The way I explained it was using point clouds, because with point clouds it's easier. With images this gets a little harder. But with point clouds we said, okay, imagine the task in front of you is I give you a huge data set of point clouds and I give you the ground truth occupancy functions for each of the point clouds. And now what you want to do is you want to train a model that takes point cloud as input and predicts the occupancy function as output. Make sense? Good. So now, just for the record, right, so one way of doing this, I'm going to show you from this perspective. From your perspective, this is the point cloud. This is the occupancy field. You could do it in exactly the same way that we just discussed with global conditioning. You could take this point cloud, pick some encoder, and code it into a single latent code, and then decode it into a voxel grid. And then again, what would happen is you would not be able to reconstruct scenes that were composed of many objects. It would fail. But now, if you do the following, it will work. And the idea is basically to preserve locality in your pipeline. So you basically say, okay, at the end of it, I need one voxel, and the voxel, for instance, needs to encode the occupancy. So what I'm going to do is, in my input point cloud, I'm going to relate this output voxel to some region in my input, to the corresponding region in my input. So for instance, here we have our point cloud. You can imagine that you draw your voxel grid around this point cloud, and then there's a number of points, for instance, that fall into each voxel, and then you say the value of each voxel is only a function of the points that fall into that voxel. And so now you can build, for instance, a point cloud encoder for only the points in each voxel. So let's say there's 100 points that fall into each voxel, and now you're going to look at these 100 points, you're going to encode them, that's going to give you a value for this voxel, and now you can use that voxel grid to decode your occupancy field. Does that make sense? Yeah? Good. Fantastic. Then we're already on our way. I put my phone away all the time. Great. So, and now, what this allowed you to do, also I should really say this paper is from Song-Yu. So these figures are from Song-Yu Peng. This paper is called Convolutional Occupancy Networks. I recommend you read it. Song-Yu is actually just graduating from his PhD. Song-Yu is one of the most well-known researchers in this area. Not for this paper, also for this paper, but not only for this paper, because he wrote like 50 papers in his PhD. And this is one of them. And all of them are fantastic. So Song-Yu is a really outstanding researcher. I think he's coming to Cambridge. I think he's going to start working at Google Cambridge, so he might be around. So Song-Yu is really, really outstanding. Cool. So this is a figure from Song-Yu's paper, and here's exactly what happens when you train that model. And so, okay, so you take point cloud as input, right? And then you produce this occupancy function, and this occupancy function is probably rendered with one of the rendering algorithms we discussed, or maybe you take marching cubes and extract the mesh, right? Like this is, but you can kind of see, right? Like clearly this model takes this point cloud as input and outputs these room scale reconstructions. And just as a reminder, if you took this and you encoded it into a single latent code and then you decode it, it would be garbage. It would just be a blob. It would look nothing like the room. I encourage you to try it out. I think maybe it's even in the paper, I don't know. Okay, and now just to be clear, why did this generalize to the task? It's because of this locality feature. It's because now each voxel only needs to store information about whatever information is in that neighborhood. And this property, you're actually familiar with it. This is the reason why convolutional neural networks work so well for images, right? So let me give you another example where you might have a better intuition for this. We imagine your task was image segmentation. Image out, image in, image segmentation mask out. What architecture would you pick to do image segmentation? You. What architecture would you pick to do image segmentation? And like, say more. Show some keywords, maybe. Okay, cool. Anyone else? What would you use? Yes? A UNet, right? Who knows what a UNet is? Some people. Okay, good. So what's the key feature of a UNet? People call these kind of architectures fully convolutional architectures. Have you heard that word before? Fully convolutional? Who has heard that before? A few people? Okay, good. So the key property, fully convolutional neural networks have exactly that property. So UNets in particular have exactly that property. What is the key difference between a UNet and an autoencoder? So an autoencoder, like the one we discussed, takes an image as input, then compresses it into a single latent, and then blows it up again to produce the segmentation mask, right? And if you train that on any image segmentation task, what you'll see is that it produces absolute garbage. And the garbage is going to look exactly like the kind of garbage you would expect from these models if you try to generalize to compositional scenes. In other words, it'll work for, you can literally make this prediction, you can go home and try it, it's going to be very cheap to train. You can literally train an autoencoder on like scenes with maybe a single object, and then there's always, in each image, there's just a single object, and it's maybe at a different position, and it looks different every time. But as long as there's just a single image, a single object in the image, it'll kind of work. It'll always give you like the approximately correct image segmentation mask. But now, if you try to take that autoencoder and you try to train it on images with like 1 to 3 objects or 1 to 5 objects, it's going to fail. For the same reason that the global conditioning fails in this case. So this is not something that is specific to 3D scenes. This happens in images as well. And how did people fix this in image segmentation? They fixed it with UNets or with fully convolutional architectures. That's why the paper Fully Convolutional Neural Networks for Image-to-Image Translation has 50,000 citations. It's because they were like, we don't compress it into a single latent. We'll just keep the spatial dimension intact throughout the network, right? And that fixed the problem. And that fixes the problem for the same reason why this fixes the problem. Does that make sense? Great. Okay, good. Cool. But you win some, lose some. So someone last lecture, I don't know, who was it? Who came forward and asked me a question? You asked me the question, right? You asked me a great question. What's your name, by the way? Aaron. Pleasure to meet you. Hi. Aaron asked a great question. Aaron was like, okay, let's assume that the size of the voxels get infinitesimally small. What information do we have? Like, imagine, for instance, you do radiance fields, like radiance field reconstruction, right? So a radiance field takes every 3D coordinate and maps it to a color and a density, right? So let's say in each voxel you store a feature, and then you do this local conditioning shenanigans to predict the density and the color, right? So in each of these vertices, you have a feature stored. And now when you want to decode a particular 3D coordinate, you take that 3D coordinate, you do trilinear interpolation, and you stick it into a small neural network, and it predicts a density and a color, okay? So now what happens if you make the voxels infinitesimally small? What information does the feature vector have to store? No, it has to store exactly the RGB and the alpha and nothing else, right? Because like if you make the grid infinitesimally small, then at each coordinate you have to store only exactly the information that you want to predict at that coordinate, which is going to be the RGB and the density. Like let's say we make the grid as coarse as possible. We just have a single big voxel. What would happen then? Then it's global conditioning, right? Then it's basically the voxel has to store all the information about the 3D scene. So clearly there's a trade-off. We can make the thing be only one voxel, and then the one latent code has to store all the information about the scene, and we're screwed, as we know already. Or we make it very small, and then the smaller you make it, the less information you have to store. And what happens, I'm sorry, but you're all sitting so far away from me, so I have to. So what happens then is that, remember the PCA plot of the MNIST auto-encoded figures. So we trained the autoencoder on MNIST digit, and the PCA plot looked really nice, right? So what do we expect if you now train this model on these rooms, right? And now let's say each voxel had the size of like, actually, yeah, imagine each voxel would be the size of like the top of this chair, like maybe this large, like maybe half of the top of the chair, okay? So now you fit this to like 1 million rooms, and now you have this latent space, right? Each voxel will now contain a latent. So you can take a point cloud now, run it through your encoder, and you will get a voxel grid out where every voxel will give you a latent code. If you now cluster these latent codes by their similarity, what pattern do you expect to emerge? Yes?
Maybe like a bunch of different clusters.
Great, yeah. Yeah, you will expect a bunch of different clusters. And what do you think will they be clustered by? Yes?
Like some parts objects, like back of the chair, the leg of the chair, top of the table, things like that.
Okay, good thinking. So what you actually see is that the model cannot differentiate between the same surface on different objects. Because imagine that this is a bad example, but imagine like you had a voxel that would contain the top of this table, and you had a voxel that would contain this floor. From the perspective of the voxel, these two things are identical because it's just a flat surface. So if you don't know anything about the texture and you only know about the geometry, then all surfaces that look identical will have the same feature code, right? They will be close. And so this is exactly what you get. So this is a different paper that was concurrent to the convolutional occupancy networks, kind of does the same thing. And what you see here is that this is the voxelization of the objects, right? Like, just to give you an idea of the scale. And what you would expect is that the feature of this part of the table will obviously be completely identical to the feature of this part of the table because they are exactly identical surfaces. And this part of the table will probably be very close to this part of the chair because they are identical surfaces. So now this latent space will not learn anything about objects. Because why would it? It doesn't have to learn anything about objects, right? Just to give you an intuition about like what these latent spaces actually mean. It just, yeah, and this is a clustering, and what you can see, right? So it was funny. I think they showed this in the paper because they're like, oh, this is cool. And I looked at this and was like, wait, this is exactly what we don't want. We would want this to be factorized by objects, like not by like random parts. But of course, it makes perfect sense that happens. So you can see here that all of these parts that are identical, they all map to the same latent code. Makes sense. Cool. Questions? Great. Okay, just for completeness sake, we talked about we talked about how you can build these voxel grids to condition your implicit representation. We also talked about these like other kinds of factorizations, like a triplane. Remember that? Instead of having a dense voxel grid, you can have 3 planes that are in space. Or you can have a single floor plan, just a single 2D grid that lies in space. And so just to give you an idea, let's say you parameterized your 3D scene as follows. You have one 2D grid on the floor, and if you want to decode a 3D coordinate, you take the 3D coordinate, you drop it onto the floor, you get the feature there via bilinear interpolation. So it's 2D grid, bilinear interpolation here, get the feature, and then you give your neural network the point and the feature, and then you decode it into an occupancy, right? So this was like the floor plan parameterization. In this case, you can also keep a degree of shift equivariance. Let's talk about that. So what would an encoder for this look like? An encoder for this would look like this. So now maybe you have a point cloud, and now you want to encode your point cloud into this latent space, which is this space of grids, right? So what would you do? You would basically say, oh, for each vertex in my ground plan, we're going to just draw a column on top of it and ask all the points that are in this column, all of these points determine the value of this point, right? Because later on, all of these points will be decoded by that feature, right? Okay, so you would basically build an encoder that would take all of these points and encode it onto the feature that you store into that 2D grid. Does that make sense? Good? Fantastic. So now here's the tricky question. What would you expect with this model? Does this model generalize to, like, do you lose any, what do you lose by doing this? Like, on first sight, you have gained something, right? Because now you don't need to store your dense 3D voxel grid anymore. You don't need to represent your scene by this dense 3D voxel grid. But now your scene is encoded only in this 2D grid, which takes much less memory, right? So that seems like a win. What did you lose by doing this? Fantastic, nailed it. Yes, that's exactly correct. So the property of compositionality that we discussed earlier, which means you can generalize to varying numbers of objects, for instance, in the scene, right? That's what compositionality meant before. You still have that property in this axis, but you will lose it in this axis. So very specifically, if at training time you see rooms where there's always two surfaces for every 2D location, because maybe there's a table standing on the ground, so that's maybe two surfaces. And now at test time, someone stacks this table onto this table, your model will fail. Because now it cannot generalize compositionally to this axis anymore. Because in this axis, it's kind of like global conditioning. In this axis, there's one latent code that has to encode everything that floats on top of it. Versus the voxel grid encoder will do perfectly fine. The voxel grid thing will be totally, I can take this table, put it on this table, and even if the model has never seen it at training time, because the local neighborhood stayed the same, and we kept this property intact, it'll generalize just fine. Make sense? Again, this is something you could test with images, which I don't know why you would want to do that, but you could do the same thing. You could like take images and encode them into you could keep them fully convolutional, or you could keep them convolutional only on one axis. So you could maybe like compress one axis to a single thing and keep the other one stretched, and you would observe the same property. You would learn that you would fail to generalize in one axis, but not in the other. Make sense? Great. Good. I feel this is, yeah, and so here's what this might look like with, okay, but skip it. Great. Okay, so I think with 3D, we now have a pretty good idea of like how this local conditioning would look like if you have point clouds as input. But of course, unfortunately, we never have point clouds as input, because where would you get the point clouds from? What do we do if we have images as input? So how can we preserve this property if, so like now we have the following property. We have our input image, right? We have an image now. And we already know one way of getting from this image to this voxel grid, which is like you build an encoder that goes to a latent code and then blows it up into a voxel grid again. But as we just learned, that would suck, because then we would lose this property that is important to us, which is generalizing to scenes that are composed of multiple objects. So what, like, so maybe this is obvious, but like, there's no straightforward way of preserving the property we just talked about, right? Because with point clouds, it was easy. For point clouds, we could just say, every voxel in the voxel grid is a function of these points in the point cloud. But now we have the image, and the image doesn't live in 3D. The image is a 2D projection of a 3D scene. So any ideas of how we could fix that? That would be more specific. Is there any way in which we can, so if you do auto-encoding, then what that means is basically you throw every notion of locality out of the window, right? Like the latent code, like you predict one latent code for the whole image. There's no part of the latent code that is particularly sensitive to, like by design, there's nothing that is special about any given part of the image. So the property that saved us in the 3D case was that a certain part of our latent space was sensitive only to a certain part in our input, which was the point cloud. So there was this notion of locality. So there was, the voxel is only a function of a local neighborhood in the point cloud. So, yes?
I was going to say that maybe you can feed it.
Yes. Did you do that in homework? Good. Fantastic. Turns out the homework was useful. Great. Good. Yeah, good thinking. So you could positionally encode the z-value. Expand a little bit more.
Yeah, so you get features from the 2D points.
Yeah.
And then you pass it through your network.
Yeah.
And you animate the output of your network with a position.
Great. Good thinking. So actually, let me just, I'm going to be dynamic, and I'm going to dynamically listen to what you're saying. So let's just jump to that solution. So in fact, that is a paper that was published in 2021. This paper has 600 citations now, which is pretty reasonable. It's a great paper. You should all go read it. But you don't have to read it maybe after we talk about it in the lecture. So here is how you solve this issue. What's the problem? The problem is that you want to locally, basically you want to relate a 3D coordinate to local features in the image. You want to somehow preserve locality. You want to say that if I have a 3D coordinate, it should somehow be related to some local neighborhood in my input image. And we already know how to do that. And the way you do that is with projection, right? You already know what the how you can relate pixel coordinates to 3D coordinates. You can take a 3D coordinate, you project it onto the image plane, and then you get a pixel coordinate. So 3D coordinates and pixel coordinates are related via projection. So the way we can exploit this is we can say, okay, let's say we take an input image, take an image as input, and we want to predict the neural radiance field from that single image, right? So what does that mean? We want to take an image as input, and then we somehow want to generate a function such that we can sample it at a 3D location, and it'll predict us the density and the color at that 3D location. Here's what we're going to do. We're going to take a 3D point, and if we want to decode that 3D point, we're going to, well, okay, first of all, we're going to take our image, and we're going to stick it through a fully convolutional neural network. So we're not going to produce a single latent code, but we're going to produce a grid of latent codes, and we can use a UNet for that, for instance. Anything that doesn't just squish it and blow it back up. It has to keep the spatial relationship intact, like a UNet or a fully convolutional neural network. So then we get, from this input image, a grid of embeddings, right? A grid of latent codes. And of course, in this grid, every latent code is a function of like a neighborhood in the original input image, right? Okay. Sorry that I'm talking about that, but I'm not quite sure if you actually learned this at MIT. Did you learn about fully convolutional neural networks in any of the classes that you took? Computer vision. Did I talk about that? Okay, good. Well, okay. Who took the computer vision class? Okay, but not everyone. So you other folks haven't had a chance to hear about that. So I don't want to make the computer vision class a prerequisite. Well, we have to think about that. Okay, anyways. So but does everyone, the people that didn't take the computer vision class, does it intuitively make sense what the difference is between a fully convolutional neural network and an autoencoder? Great, fantastic, good. Okay, so that's okay, good. So I hope, please, this is like totally reasonable not to know. So please, you also just come after class and find me. I'm happy to explain it. Okay, so this is a fully convolutional neural network. And then when you have a 3D coordinate, what you're going to do is you're going to take that 3D coordinate and using the camera intrinsics and extrinsics, the camera parameters, you will project that 3D coordinate onto the image plane. And then you're going to do bilinear interpolation to get that feature in the image plane. And then you can take that feature and you can give it to your neural field. You can use it to parameterize your neural field, right? So you could either use that feature, stick it into a hypernetwork, predict your neural field. In this case, this paper did conditioning via concatenation, which means for that 3D coordinate, you're going to just concatenate the feature that you get from the image encoder to the input to the neural network. And then the neural network will decode it into an RGB and an alpha value. Make sense? Fantastic. Okay, yes?
Is there a way to deal with conclusions?
Is there a way to...
Like in the sense that that back projection for a 3D coordinate only works if that 3D coordinate is seen?
Good question. So the question is there a way to deal with occlusions? Because, so I think what you're asking, Cairo, is actually a fairly deep and annoying question. So let's say we have a car. Cars are our favorite object. So this is the top view of a car. I can't even draw a rectangle. Anyways, so so here's a car. These are the wheels. Let's just get some intuition for what's happening, right? Okay. So here's an image that we captured of this car. Let's say, okay, this is too big. I'm gonna make it a little smaller. So this is like this is the camera. So this is, you guys can't see this, can you? Can you? Okay, good. So here's the field of view of the camera, right? Okay. So the car is going to look something like, maybe like it's projected onto here, right? Okay. So now I have colored things, but I left them in my office like a genius. Now, just to recap what we just discussed, we're going to draw it again in 2D. Let's say you wanted to decode the RGB and the alpha of this point here. What you're going to do is you're going to take this point coordinate, you're going to project it onto the image plane, get a feature here, call this feature F, get this 2D coordinate, call that X, take these, stick them into a neural network, predict color and alpha. Make sense? Good. Now Cairo is asking a great question. Let's say we wanted to decode this coordinate here. Now if we project this coordinate onto the image plane, of course we can find a pixel coordinate that corresponds that corresponds to, it's not a straight line. Of course, we can find a pixel coordinate that corresponds to that 3D coordinate, or right? Like it's going to be somewhere here. Great, easy. But what is this pixel value actually going to show? It's going to show the front of the car, of course, because the back of the car is occluded. So now, what gives? That's annoying. So, yes?
Well, I don't know. Can you use volume rendering as well? Because you know, like if you already have some sort of model,
Right.
built in, like you know it's already occluded.
Smart. Okay, so what you're saying is like if we already knew what kind of object we want to decode, like if we already knew that it was a car, or it maybe emerges during training, then we might use that information in a smart way. The answer is yes, you can do that. And there are papers that do this. The papers that do this exploit usually symmetry. So they say, we know that the car is symmetric around this axis, so if we want to decode this feature, we're going to actually mirror it onto here, and then this, and then that's the feature we're going to actually use.
I guess I was saying that if you're like training your volume at each point, you can use volume rendering, right?
But for that, you need the neural field first. It's a chicken, unfortunately, it's a chicken and egg problem. So in order to do that, you first need to, no one saw that, great. Okay, good. So yeah, good thinking, but you don't have the thing yet. So unfortunately, you can't do it. So the problem is, but you realize the problem, of course, that the thing that the pixel is going to show is actually this feature, which this feature has zero information, apparently, about this wheel, like, because you're not, okay. So yeah? Yeah, like let me finish this, and then we're going to get to your question, yes? So what happens in practice is that the neural network just kind of, it's like, this is certainly a problem. Like if you could somehow get around this, it would be great, but you can't easily get around this. And what happens is it still works, and the reason why it still works is because the neural network will just learn, in the fully convolutional neural network, the neural network will just learn to take information from this pixel and write it into this pixel. That's what's actually happening. So the neural network would just say, okay, here's the wheel. I infer this is a car. I recognize that this is a car. The car is approximately in this position. Therefore, the wheel is over there. Therefore, I'm going to take the features like it's basically deep learning magic. The neural network will just write the correct feature into this location by reasoning about the neighborhood in the image. That's what actually ends up happening. But it is a problem.
So like if the object, like right now we're talking about a single object case.
Yeah.
But if I was to put like, I don't know, another car behind that car.
Yeah.
And we're talking about like what's the point of the other car.
Right.
And like it's like completely different color, completely different like then it couldn't do it, right?
That's correct. So yeah, if the, well, like let's think about this. So let's say there was another car here. Okay. As long as the other, it's a huge car. As long as the other car is seen, right, then it's no problem. So like even, let's say this wheel, right, the neural network sees this car in the back and it's like, aha, I infer that there's another car. The car has to extend in this direction, so the wheel is here, no problem. But if the car is occluded, then there's nothing you can do. But these are all good questions. And now let's talk about one particular case. So we just talked about a certain trade-off that you get when you go from a voxel grid to a floor plan, right? So what do you expect the generalization ability of this thing to be? There's a, like, just apply the same concept to here. So like we just said that in the point cloud case, by having, instead of having a voxel grid going to a floor plan, you basically stop having generalization capabilities in the z-axis, right? Because now for all of these 3D points, you're using the same feature. So of course we have something similar here, right? So what would happen is that if at training time, there is a fixed number of surfaces that you see along the z-axis, at test time, you will not be able to generalize to an unseen number of surfaces. So for instance, if at training time there's a maximum of 2 cars that are overlapping each other, then that, so like for instance in this case, right? So let's say at training time you sometimes see 2 cars and you supervise it, like so you always supervise it with them, so no problem, that will work. But now if at test time we put another car behind here, that will fail, guaranteed, because the model cannot generalize to an out of distribution number of things along the z-axis. Womp womp. That sucks. This is, to the best of my knowledge, kind of an unsolved problem. I have thought about ways of solving this. You can probably also, if you think really hard, you can probably also come up with a way of solving this, but I haven't written a paper about it yet. I'm not sure if it's worth one. Yes?
Aren't you supposed to use a Y ground plan and then a ZY ground plan? So take two pictures of it and then use.
Yeah, if you have another picture, that solves the problem to a degree, right? Actually, we're just going to continue talking. Great question. So yeah, if you have another picture, you can, what could you do? Yeah, I don't have a slide for this, but imagine you had another picture. And now, imagine you had another picture, and now you wanted to decode this coordinate. What could you do? You could project this coordinate onto this image, and now you just take the mean of these two features, for instance, or you, yeah. But that's not your question, is it?
Well, yeah, but I mean, this is for bilinear interpolation twice.
But like the assumption is you only have one image as input, right? You just get one image. That's the image. I give you an image and I want the nerf from it.
Okay.
I want to do 3D reconstruction from single images. That's the problem setup. So this is really literally the input image. Yeah. Okay, yeah, and so like now just to put an image this, so this is my paper from 2019. This is PixelNerf from 2020. And this is exactly the case we just discussed. So this is my paper trained, like both of these methods are trained on single objects, right? On objects on 3D scenes with just a single object. And on the training set, that works perfectly fine. And if you try to reconstruct single objects, both of the methods work just fine. But now, if you go at test time and you give it two objects, my model does this, because it just has a single latent code that encodes the whole scene. And PixelNerf, the model that we just discussed, does the thing that you see on the right, which is the correct thing to do. And why is that? It's because, and note that these images are picked in a particular way, right? These perspectives are chosen in a particular way. These perspectives are chosen in a way that these two objects rarely overlap behind it. Actually, I'm not sure if this was trained on two objects or not. It might have even been the case that this was trained on two objects as well, in which case my thing would have still failed for the reasons we outlined. But you can see that the input images here are always picked such that the models don't overlap. Because if they overlap, then you have exactly this problem with generalization. Versus here, right, like the convolutional encoder will just encode this, and because it's shift equivariant, it'll just nicely produce separate features for these two objects. So all good. Okay, whatever. Are we going to talk, or should we talk about that? Yeah, I'm going to talk about something else instead. Let's see. So we skipped a part earlier. So this is everything we just talked about was assuming that you parameterize the 3D scene via a neural field, right? You represent the 3D scene via a neural field, like a neural network that you sample at a 3D coordinate. But we discussed before what were the limitations or what were problems with neural fields. They're really slow to render. That was one of the problems, right? This is also true for this model. Imagine what you have to do what do you do when you render this thing, right? You have to sample hundreds of points along each ray, or thousands of points along each ray. And for each of the points, you have to do a forward pass through this neural network. So for each of the points, you're going to project, get the feature. That's really cheap. That's like a lookup in a voxel grid. That's very cheap. You do that, you get the feature, but now you have to do this forward pass through the neural field, which then decodes it into an RGB and an alpha. And that turns out expensive. So that's bad. So we already discussed a way of how this used to be fixed in normal neural fields, which is you can instead just use a voxel grid or something, right? The voxel grid is much cheaper, and the same is also true here. So instead of just doing this with like a neural field here, you can also just instead say, well, we're going to take our image, and from this image, we're going to just predict a voxel grid. We're just going to predict a voxel grid that discretizes our scene, and now when we want to render it, we just have to sample this voxel grid, which is much cheaper. How do you do that? The way you do this is called via unprojection. So just to give you an idea, and this sounds fancy, it's actually very easy. Basically, let's say what you do is you initialize a voxel grid in free space, and you just make it empty, for instance, or you just whatever. And now you have your image observation, right? Like this is the camera, this is the image. And now what you're going to do is you shoot array. Intuitively, you shoot array through every pixel, and you just copy the value of that feature into every voxel along the ray, right? So that's what these colors indicate, right? And now there's of course a problem, which is now all these features are identical, which is not going to help your case. So now usually what you do is you concatenate the depth with each of them, and then you run like a single 3D convolution on top of the thing, which then makes it varying with the depth. So just let me be more precise. So this step is intuitive, right? It's kind of annoying. I must warn you, it's annoying to code up. It's like, it really sucks. It's like very annoying. You have to do like scatter and gather and all of this BS, but you can do it. But now each of these features are identical, which is obviously not great. So what you would do is you would, in addition to just copying the feature into here, you would also concatenate the depth at this position. So here you concatenate the depth, here concatenate the depth, here concatenate the depth. And now each of the voxels has a different feature, and now these features are somewhat meaningful. Okay, so here's actually a paper I wrote from 2019, which this is a video that I lifted. This is a screenshot that I lifted from the video, which is what I did in that paper. So I had exactly that screenshot. Sorry, this is mostly for nostalgia. And here's a paper from 2021 that does this. So this is, I'm just showing you the figure from the paper. So here, exactly what we just discussed. You have an input image. Now you encode the input image with a 2D UNet. And now you do this unprojection operator, gives you a 3D voxel grid. Now you run, in this case, a 3D UNet on it, which is just a 3D convolution. And then that gives you the voxel grid directly. And then you can render the voxel grid. And now the rendering is going to be really cheap, because the rendering is just lookups at a voxel grid versus doing a forward pass through the neural network. Yes, question?
Is your output limited by the voxel resolution?
Yes. So this is one way to think about this, is that you're trading off the compute for rendering and inference time. So what does that mean, right? So in this case here, if you look at this case, sorry, now I do imagine we forget about the voxel grid, the pixel nerve case, the case where you use a neural field to decode it. In that case, the inference, so like the reconstructing all the features that parameterize the scene is very cheap, because reconstructing all the features that parameterize the scene is literally just getting the features of the image. You just do a forward pass to the image. That's really cheap. And now the thing that's expensive is the rendering. Every time you render, you have to sample your neural field. And here, it's kind of flipped around, because here now, the reconstruction gets much more expensive, because you're reconstructing the 3D volume already in the forward pass of the neural network. So you go from this, and then you reconstruct the voxel grid, and that is expensive. And as you say, it's limited by the resolution of the voxel grid, for instance. But now the rendering gets really cheap. But it is exactly the case that technically here you're not limited by it is exactly true that here you're not limited by the resolution of the voxel grid. Like this thing doesn't have a voxel grid resolution. In theory, the resolution could be much higher in theory. Yeah?
In the voxel case, it's you.
Great. This is good thinking, but notice that we only have one image here. So from a single input image, you can't do triangulation. In the two image case, you are exactly correct. If you had two images, then what would be the easiest thing for the neural network to learn? The easiest thing for the neural network to learn is, like, imagine you produce two of these, like you have two images and you produce two of these voxel grids. And now you give both of these to a neural network. Now all the neural network has to do is, like, it looks into each voxel and it checks whether the two values are the same. And if the two values are the same, it's like, aha, I have found the correct thing. Right? Good thinking. Yeah. Does this make sense? Great. I just dumped figures here to tell you that this is still relevant today. So here's another figure. This is from CVPR 2023. So this paper came out 6 months ago. So we're at the cutting edge of computer vision now. And this paper here, this is actually a diffusion model. We're going to talk about this in 2 lectures from now. This is much more complicated. But actually, there is one part that is exactly identical to what we just discussed. Namely, it takes an input image, input view here, sends it through an encoder, and then what this thing here, latent feature field W, is supposed to mean is that from this image, they infer a voxel grid with resolution 128, 128, 64, 16, where 16 is the feature dimension, 128, 128 is this, and then 64 is the number of depth, right? So this is exactly what they did. They literally took the input image, which in their case, let's say, had a resolution of 128, which indeed it did, and then they just discretized this thing here. And they said, oh, we're going to have 64 along the depth dimension, and we're going to have 128 along the pixel dimension. And that's exactly what's happening in this paper. And then you can build diffusion models with this, but that's coming up later. Okay, cool. Okay, so does that all make sense? Great. Then we're going to spend the last 15 minutes of this lecture to talk about, now we're going to, in preparation, so this lecture is basically only on this local conditioning. The next lecture is going to be about transformers and about how transformers play into this, because there's something really interesting and fun going on with when you add transformers to the mix. So today we are breaching these two things a little bit, and we're going to talk about a model which is kind of looks a little bit like the models we were just talking about, but it also has some transformer parts. Is everyone comfortable with transformers? Do people know how transformers work? Who doesn't know how transformers work? Yeah. Okay. You also don't know? Okay. Good. We will discuss it. You also? Okay. Good. So we will discuss it in the next lecture a little bit. For now, I think you will have no problem understanding what's going on anyways. So it'll just some of the words. Okay, so here's a paper that we wrote, actually CVPR 2023. This used to be the state of the art, but a new paper came out yesterday, and now it's not the state of the art anymore. But it used to be the state of the art. When it came out, it was. So here's a paper that takes two views as input, and from these two views, it does novel view synthesis. So two images as input, novel view synthesis out. Okay, and so now you maybe can get an appreciation for where we're getting with this, right? So far we were looking with these little toy cars. Of course, we're far beyond toy cars in the real world now. Not actually, I mean, this has happened in 3 years, so it's noteworthy that this thing going from toy cars to this took 3 years, which is not very long. It's kind of cool. But you can see this is kind of getting there, right? So like two images is input, and now we can do novel view synthesis, and it looks pretty reasonable. So how does that work? So in fact, the model that we just talked about, the models we can just, so here at the top, this is actually a slide that I have from a talk that I usually give about this paper. So here at the top, you can see the model we just talked about. This is one of the baselines for this paper. And then these two we didn't talk about. And I'm afraid we're not going to get to talk about them, but they're related. So you can look them up yourself. So we could literally think of a way of using the model we just talked about to solve this problem, right? So like you now know of at least one model that has this input-output behavior, which is exactly the model we just talked about. We just talked about it with a single image input, but now you just have two images as input. You want to decode a 3D coordinate, you project it on both of the images, you get the features at both of the images, and now, I don't know, you take the mean, you give that to a neural network, and then it predicts the RGB and the alpha, right? And that would be one way in which you could adopt the model we just talked about to solve this problem. I'm just saying that the model we just talked about could solve this problem already, right? Okay, good. But now it turns out that wouldn't work very well. And here's a few subtleties that you have to keep in mind when you deal with stuff like that. The first one is, okay, actually let me really make sure that you guys understand the baseline that I just described. So because the model we just talked about, the pixel nerve model, it really only works with a single frame. So let's just make sure you understand how it works with if you had two input images. So let's say this is our car. We just discussed how you can reconstruct this from a single input image, right? You take the 3D coordinate, you project it onto the thing, you get the feature here decoded. How do you generalize this to two views? Now you have two input images, like this one and this one. And now what you do is, instead of just getting the feature from this view, right? So take this coordinate, get this feature here, feature, and then you get this coordinate x. Now we're going to indicate this with a 1, so it's feature 1 from view number 1. Now you just have also a second feature from view number 2, and whoop, just take that in here, feature 2, x, put that into your neural network, right? Does that make sense? Straightforward extension. Okay, so you can just use this model, you can train it, works totally fine, or like you can train it, it is a reasonable thing to do. That wouldn't work very well. So what's the limitation with that? So when you deal with two images, and this is getting at the triangulation point that you just made. Who made that point? You. Ah, thanks. So two input images. So let's say we take these two input images as input. No, we do know the camera poses. We assume that we know the camera poses, which is a big assumption, but like let's just roll with that for now. So we have these two input images. What's the correspondences here, right? This pixel here corresponds to this pixel here, right? So it's like okay. So let's think, let's get some intuition for what this model actually does. So this is now a little bit subtle. But okay, so the model we just talked about, the model that reconstructs a car from a single image, what do you intuitively expect this model to do? Actually, I'm going to answer the question for you because we only have 10 minutes. The model will do one depth estimation, right? For every pixel that is visible, the problem boils down to estimating the depth of that pixel. If I look at a car and I want to reconstruct the 3D object, for every pixel that I see, I just estimate the depth, I'm done. And then for all the pixels I don't see, it's more complicated. For all the pixels I don't see, I have to do some shenanigans with like weird stuff. But at least the visible side is easy to think about. Okay, but now there's something funny going on. Imagine for a moment that you're in this model that we discussed here, right? Like this straightforward extension. These two images, they are encoded with the same convolutional neural network. You use the same encoder to get the feature maps for these two images. But you encode both of them separately. Like the encoder just, when it encodes the image, it just looks at that one image. It just takes that image as input and it just encodes that one image. And then the only time the model actually aggregates the information from these two views is when you concatenate them together to predict the final RGB in the alpha, right? Okay. Why could that be problematic? It could be problematic because think about this point here. These two models could estimate two different depths for this point, right? Which would make sense because both of them are probably uncertain, right? Both of them don't actually know what to do. So both of them will be like, could be this or it could be that. Okay, so if the depths don't match, then you are in a little bit of a pickle. Because if the depths don't match, then let's say you could take this point here. And now let's say okay, this is actually a bad example. No, actually perfect. So you take this point here, and now let's say this model here, this encoder here predicted that this in fact was the correct depth. It said like, oh, this is the depth at which I think this thing is at. And this one here, let's say, made the correct prediction, which said the depth should be there. Then the model can never fix this. It like what it would do is it would be like, okay, when you decode either of these, it'll just be like, okay, I'm uncertain. Like I can't like which one is it? I don't know. So I'm just going to make it blurry. I'm just going to do the best guess, which is I'm going to like make both of them like half transparent, and I'm going to make it a blurry mess. Obviously, that's not the ideal solution. So an easy like kind of fix with a sledgehammer is you ignore this. You just build a multi-view encoder. So you build an encoder that can look at both of the images at the same time. And how you do that has some subtlety, and you should. But the dumbest way you can do it, which is what we did, is you literally build like two separate convolutional neural networks, and then you have some attention that looks at both of the images during the encoding step. So you basically encode both of the images separately, and then you have cross-attention or like self-attention between each of the layers of the two encoders. And now imagine what can happen, right? And you also have to tell it about the camera pose. So you give it both the camera pose and you give it and now what happens, right, is this encoder will encode this image. I'll be like, okay, I'm looking at this pixel right now. This encoder will encode this image, and then they talk to each other. So this encoder will be like, hey, I have this pixel here, and my camera pose is this. Do you have something similar? I see you have the same thing, and your camera pose is this, and then it can do triangulation. That's exactly what it's going to do. It's going to be like, okay, our things are inconsistent, so we're going to fix both of our depth estimates such that they're consistent, and then, ta-da, now we can encode the correct depth. So if you do it without the multi-view encoder, this is what you get. So this is basically kind of like this is what you would get with vanilla Pixelwerf paper. So as you can see, these renderings are kind of a mess. And the artifacts that you see, I'm not sure if this is very visible. The artifacts that you will see are literally going to look like stretches. So basically, the model will basically just blur along the depth axis because it's unsure in the depth axis, so it's just going to blur along the depth axis. Questions? Great. Okay, and with the depth encoder, it looks much better with the multi-encoder. Great. And then the second part. And then the second part is the renderer. This is a little bit subtle, and I don't know if we have to talk about this. I think if you're interested in this, you can just read the paper. But basically, the second part is instead of doing volume rendering, which is very expensive, you can just approximate rendering via a transformer that looks at all the features as well. So if you want to render this ray, right? If you want to render this ray, what would you do with volume rendering? You would sample these points along the ray according to the near and far plane, right? You would say, okay, I want to render this camera near plane here, far plane here. I discretize the space in between. I get all of these samples. And now for both of them, you would project them onto the two images, get the features there, and render. But it turns out that's a little stupid because if you set the near and the far plane during rendering just willy-nilly, that ignores the fact that you know which part of the 3D scene you have information about. The only part of the 3D scene that you have information about is the parts of the 3D scene that you have seen in the two images. You haven't seen anything else. Like if there's no point, right? If your, let's say your field of view for this camera looked like that, right? And now, again, this is so much mess. Okay, so yeah, this is easy. Okay, so let's say you have a camera here. This is your observation, and your observation looks like that. And now you want to render this ray. Like this is the ray that you want to render. Obviously, there is no point in sampling these points, right? Because these points are not projecting onto the image. You don't know anything about these points. Like, what are you possibly going to? There's no information there. Like the only thing you should be thinking about is the points that actually do fall onto the image. Those are the only points you can say something about. And so there's a lot more subtlety, but this is basically the key idea here. So you sample these points according to which points you actually saw in the 3D scene. Doesn't matter. That's important. Back then it was really fast. It was really nice. This is what the renderings look like. You already saw these. And then just to give you an idea of what the baseline looked like. So PixelNerf is exactly the model we just talked about. So PixelNerf is the model that doesn't have any multi-view encoder or any of this stuff going on. And you can see it doesn't work very well. And then this is the model that we just talked about. Looks much better. Cool. I think, in fact, that is the last slide. It is. Amazing. So I'll release you on time. Thanks for coming.